Yes, so given got such a nice introduction already, I can skip over this slide and jump right into the tool. As the workflow and the tooling, if you have never seen it before, most likely will be a bit unusual to you. I will first tell you what it is not. It's not a high-level synthesis tool. It's not a compiler. It is not your typical generator framework, although you can build generator frameworks with it. Most of all, it is also not visual. Doing visual stuff in FPGAs is something like the first trap of vendors to get you logged in. So that is counterproductive in this context. But what is it? It is a user-extensible framework written in C++ that, for a given RTL design, interprets its structure and features specified in text-based model files, composes and maintains, like based on these model files, a fine-grained model in a SQL database, and then is able to write VHDL and C++ code based on it. Taking into account, that was one too fast, taking into account manual code contributions of previous design versions. So if you think of regular, code generators, that's maybe quite a difference already. Don't worry, I will get with examples much more into, bring you closer to see how that works in the next slides. What are the key features? Key features are clean ergonomic source code structure that is enforced by using the model-based approach. It has lots of advantages, starting from tasteful naming conventions, but the list goes on. Like if you think of, in this approach, you always are sure which process controls which signal and which port. You have the model description to the side of your project, so that reduces your documentation effort, makes it easier to grasp what the project does after you haven't looked at it for a long time, or if another person looks at it. It also has a parametrized template database in the back of common stuff, but you can extend it. Custom templates are also possible. Maybe if you think of typically template-based things that you might imagine a file with placeholders where you insert placeholders, this tool can go way beyond it. Like if you have a template for a complex subsystem you want to reuse in or use and reuse in your projects, you add it as a C++ source file that you compile into the code, and then it has access to all its surroundings. Like it can see, I'm in a microchip design, I'm in Xilinx design, I'm in an Altera design, and then it can derive different primitives based on that. Things like that are then possible. And then the scope extends beyond the FPGA domain. So there is a sister tool that is responsible for also generating, the pointer doesn't work really well, but there is also a tool that generates in a similar fashion a multi-threaded Linux daemons that have everything up to web-based user interfaces. And you can use them together, you don't have to use them together. So what changes in your developer workflow, maybe is what you're wondering. If you agree or come to the conclusion it might be smart to use this approach, the idea is that it should stay at mostly the same. It should just be augmented by some helpful features to help you save time and make cleaner code. The thing that is added to your developer workflow is what I call source code tree iteration. It is shown here. If you think of a regular source code generator, usually you have the input to your source code generator, you change a parameter in there, you run the source code generator, and you get an output, and that's it. That is, of course, very disadvantageous if you have a huge project with many modules and the source code generator just overwrites everything. So that is not the case here. From the second iteration or the second version of your model, you don't only feed in the updated or new model files where you want the change to take place, but you also feed in your existing source code tree, and then the Wisnium tool will extract your manual modifications to the source code tree and reinsert them in the newly generated source code tree of the next version. So I have 3 examples of how such modeling could look like. And there you will also see how the model files look like. I warned you they are text-based, but then text-based is also good because it's diffable, you know. And this you can probably only read in the front rows, but I mean, you have the presentation online. So the concept of these input files is always the same. You have header lines, which are here highlighted in blue. And you have content lines which are black, and by indentation you achieve that something belongs to something. To make that more clear in this example, here is defined a unit in Wisnium slang, which is basically an IP core that you are working on. Indent 1, and then you say I have a client module called client in there, and the submodule that is CRC that is based on a template, the CRC template. And what is changed in this model file right now, what I want to take Wisnium into account, what I want Wisnium to take into account is I changed the polynomial. So it used to be some number. Now it's 1, 2, 3, 4, 5, 6, 7, 8. What it does with this input is twofold. Well, first of all, it will, where this subblock is embedded, change which CRC is used. And second, it will also write the corresponding VHDL code that depends on the polynomial, right? So that is one example. I have then 2 more model files we are going course to find here. That modular description is the top level view for designs here as an any RTL tool, I guess. So going one step further, it is possible to attribute commands to individual submodules in your FPGA designs, commands which you can then invoke from a CPU host, which will be slides of their own later on. So here I have a similar example. I add a new command that's called do something with the invocation parameter what. And that is the input. And the output is that the concerned module gets a new handshake, request invoke, acknowledge invoke, along with the parameter do something what. And then finally, in the most exhaustive model file that you can put in any Wisnium project, the fine structure model file, you can do everything down to state machine and steps in state machines, conditional steps. You can model all that. And that's what I've done here. I have a state machine that's called traffic generation. It had a state, no, it gets a new state that's called abort, and the state abort is now reached from the state pause under the condition that problem occurred. And the output for this can be seen here. So I hope this made it a little bit more clear, but the ultimate thing I have for you here is a video showing you how this looks like. So you are developing your HDL code that you see in the back. It's like a Visual Studio Code. And then on your workstation, it can be the same computer as well. You have the Wisnium daemon running. That's the terminal on the right-hand side. And then there is a little Java tool, so it's cross-platform, where you can initiate this process of source code tree iteration. And I guess for this I need the mouse. So what you basically see here, you connect to the daemon, you select your project, then you point to the model sources on your hard drive, and then you press step, and then it is doing the whole magic of composing the modular structure, reading and parsing and interpreting all your input files. Then it also took the existing source code tree and updated it to the new version and downloaded it back to your computer. Okay, then there are some more things to help starting using the tool, and also for myself and a small team that sometimes helps working on this, to validate the cross-vendor benefit, right? So we have a project that is a tabletop 3D laser scanner that serves as a reference, and our aim is to implement it in all possible FPGA platforms. We try to keep that up to date. You would never just enter our office and all of them are running, but we try to give each platform a chance at least once every 2 or 3 months to be fully up to date. So it is a nice example because it is not too simple, it is not too complicated, and what it does is you have this turntable where you place an object and a camera looking at it, along with 2 line lasers there to the left and to the right, pointing at the object. Then you turn the turntable, switch on and off the lasers, and you identify the trace in the camera image, and then eventually you get a 3D representation of the object. So there are 8 FPGA-based platforms. You have Xilinx with and without SoC. In the SoC case, Zinc MP and the first generation Zinc. PolarFire SoC, Lattice to the left lower corner, 2 Altera versions, and top right, Efinix Titanium. Yeah, that would be just to show that what the design comprises. I mean, there is some pipeline algorithm in it, preview image generation, access to not so simple hardware blocks like the MIPI to connect to the camera, then HDMI monitoring, DDR memory access, and PCI Express for live image streaming. Not all platforms can support the whole functionality, but they would use subsets of this. Okay, so that was the first part of my presentation. Now I have shown you what is the tool that allows you to become more vendor agnostic than you probably are right now. And now we just have to collect the perks of having this tool, and I present 3 of them. So based on what you have seen, you can now easily imagine that you can become completely vendor, but also interface agnostic if you talk between a CPU host and your FPGA subsystem. This is not even a pure vendor agnosticity case because the interfaces are already quite standardized. I mean, AXILite on a PolarFire SoC is very much the same as from a user point of view, as AXILite on Sync MP, or even the Phoenix soft core they are providing, the RISC-V soft cores. But the agnosticity here comes in through that you have a host interface template in the Wisnium system, where one parameter is phi type, and if you want to have AXILite 32 for a SOC one day, and SPI or even something like UART over USB the next day, then you just change this one parameter and you get, you still have connectivity from your host to the FPGA. So this is the most comprehensive template maybe of the whole project, because it allows you to be synchronized between your host and your FPGA if you invoke commands or want to do something triggered from the host in the device. You can also do bulk buffer transfers. Yes, provocative thought. I mean, it also overcomes, I would say, I think a bit outdated idea that if you want to configure something, you write some value to some register and hope that you wrote it to the right register at the right time. Here you just get a function you invoke in C or C++, and then you leave it up to the FPGA to decide if it wants to accept this command. There is a straightforward CRC-based protocol where I don't have to go into details. Basically, it goes back and forth between host and FPGA with acknowledgements and CRCs. It works for command invocations and small buffer transfers, like several kilobytes for configuration, which you can pass across AXILite or even UART. And then, as we have this source code co-generation, you get for free a command line terminal where you can invoke all these commands for debug purposes. And you also, if you think back to the Wisnium SPE part in one of the first diagrams, you get a tool that runs on your Linux host that provides this through a web-based user interface. Perk number 2, that was something where there's a presentation in very much detail online where I would refer you to. So I started using this privilege of not being bound to a vendor to encapsulate and wrap the 4 not super high-speed interfaces, but commonly used not so low-speed interfaces, like being a step bigger or faster than SPI, but a step smaller than gigabit, where you would need gigabit transceivers. And the point here is simply that this is another trap from the vendor, so to say. Once you decide to use PCI Express block from Xilinx, you will think twice before you switch over your design to another vendor, because there is too much, let's say, vendor-specific stuff in there. And the idea here is to just replace, to have wrappers for just the core functionality of what PCI Express, MIPI, and the other two do, and then go from there. So the blue block is always the template that is the template in Wisnium. You see a bit from the diagrams what it does. Yeah. Also here, like a DDR memory access mutex in the end. It is a quite nice thing to have. On top of making you vendor agnostic, it also allows you to share access to DDR memory with an arbitration algorithm. Finally, that's a bit work in progress, but it is another thing where vendors get you, like, I mean, they get you locked in. So as you have seen, like this interface between CPU and FPGA, now there is no reason to do anything out of the ordinary or vendor-specific if you have standardized communication between CPU and FPGA. Then you can as well put things like spying on your design and debugging it into that. And there's a bit another template that is now part of the system where you can monitor state machine states and their sequence, but also their coverage from various modules, and then you can read it out to the Linux host through aforementioned auto-generated interface. And then you get readout like this, but which states did you cover and which order did they show up. Since recently there is also a start of having something like VCD output for GTK wave. And I think it would be a good idea if this could replace everything what the vendors do for you. But then have you logged into their IDE. Okay, resources. There is stuff available online. If you are wondering, and probably some of you are, how many people are using this tool, I will answer the question without it being asked so far. More than one handful and less than two handful. So if I go back full circle from the last session of the conference to the first session of the conference, where Javier mentioned, what is a good open source tool, and he said, bad open source tools are only those which are not maintained. Here I can assure you, even if you don't see frequent updates on GitHub, they are very well maintained because if you think of these 1 to 2 handful of people, our efficiency and our productivity very much depends on them. So that would be my final remark here. Other than that, I thank you for your attention, and I'm happy to answer questions.
Very nice presentation. Thank you very much. I had a question about something that you touched already, and you mentioned that if you are using Xilinx FPGAs, for example, and you have a PCI Express core in there, then you think twice before going to another FPGA family, right? And so I really appreciate this thing that you put a layer on top of the IP, for example, that makes it agnostic. But how do you actually handle when you set your FPGA? For example, let's say that you want to go with Xilinx. How do you configure the specific Xilinx IP to do that?
Oh, okay, yes, that's a good question. So yes, it's true that the Xilinx core IP, it remains in the design, so you have to configure it currently manually. But what the tool can help you with, kind of, is you can write down in the template for the Xilinx core this and this parameter is necessary in order to function. I'm sure it could be automated with tickle scripts, but currently there is nothing like that.
Thank you.
Hi. I think this aim for going vendor independent is a nice idea, but I think you pay a price. One price clearly is performance, because if you really want to exploit the full performance of your interfaces, you have to use the vendor IP, and the other is resources, because you obviously have some adaptation layers. And the problem with the vendor independence is still the underlying IPs still need to be configured. So somebody has to do the work. So let's say there's a new Xilinx family coming out, you have to generate all the wrappers for your project. And this is not just one vendor, there's like 3, 4, or 5 vendors, so this is a lot of work to have something like that, maintained.
That is very much true if you talk about, I mean, the first part, that you do not get the least bit of performance out, or not the feature that vendor A has but vendor B doesn't have. Especially if you look at the interfaces, the 4 interfaces I mentioned here, there are, I wouldn't say fringe cases, but yeah, in the end, fringe cases where you pick your vendor just because you want their exceptionally fast gigabit transceiver. But with PCI Express or DDR memory access, the case, from my perception, is very much different. Every system, I mean, lots of systems you come across need some PCI Express access, and you don't need the very least bit of performance. You just need to have an established PCI Express data link to a host where you can exchange data. And that, I didn't mention it, but it was written there. So the aim of this vendor agnosticity part is to cover the core functionality, like the basic functionality. And then it is not that bad anymore that somebody has to read like the whole user guide of a newly code that has been newly made available. And in terms of overhead, many vendors are relatively far in that their interfaces already are AXI stream and AXI, so there is not so much to wrap anymore. For others, I agree that probably it adds a bit of functionality, but of resource use. But on the other hand, I was talking about mid-range and bigger devices here, so I've never seen that being a bottleneck.
Any more questions? I have a curiosity myself. At what point is one supposed to do the simulation verification? First, you generate your RTL code, and then if you port it to another, so you see my question.
Sure.
Do you simulate it independently for after all the porting, let's say?
I mean, there is your regular workflow of of just RTL simulation. There, the tool can help you to write a test bench that is anyway vendor independent. If you want to funnel in the vendor IPs, then you just have to do that manually.
Okay, so I can only simulate the part that doesn't include any IPs.
No, I mean, if you want to include the IPs, then you...
then I lose vendor independency.
Yes.
Yeah, okay. Yeah, that
yes.
makes sense.
But I mean, you can get very far without that. Like, yeah.
Any more questions? So we can thank